is I want to point out that we now have three really different ways of thinking about this problem, right? And two of them are like advanced and long, and one of them is basic and quite fast. So like I showed some people this in my office earlier today. So I want to show everybody to like make sure we all understand like all the different approaches that we have in the class to understanding this right now. Now, of course, there's approach 0, which is something you would never do, which is parameterize this thing, which would be awful, right? I mean, essentially what we're trying to do here is, you could, I guess, if you wanted to, try to put e to the, like 4e to the it into this thing and try to hack it down, but good luck, right? You're going to get something out the other side that's basically impossible. So the key to the entire class, the key to the whole class and why all the theorems in the class work is that you guys could tell me what happens to this integral, z minus a, if c goes around a. What is that integral equal to? 2 pi I. What is this integral in every other case? Z minus a to the n dz, where n is any other number other than any integer other than -1. What is that integral? 0. C goes around a. So in every other case, this integral is equal to 0. That is the key to everything else in the class. Why all these techniques work is ultimately in the background, after some hand waving about switching integration and summation around. It's essentially just this, right? This idea underlies all the rest of it. So here is the big insight that comes out of the Cauchy theorem. If you are integrating a function like this around a contour, there's no way this is going to work, right? Okay. So this is modulus of z is equal to 4. I've never seen this color before. Let's try that one. Okay. And you have a singularity at 0 and a singularity at 2. So there's a singularity at 2 and a singularity at 0. The Cauchy theorem says, without any sort of like long explanation of what's going on with the contours in and contours out, this is equal to the integral around these two paths. So what the Cauchy theorem directly implies, and we're going to use this for two of the methods that we're talking about. What the Cauchy theorem directly implies is that integrating around the big curve, the integral of f of z dz around the big curve is equal to the integral around each of these two little curves added up. Say, I'll call that C0 because it goes around 0, and I'll call this C2 because it goes around 2. This is equal to f of z integrating around that little circle at 0 plus f of z integrated around that little curve at 2. This is a direct consequence of the Cauchy theorem. If you want to see why, imagine that what's happening here is you're just doing this, right? You're going around, and then you say you cut in and you go to make sure that orientation is preserved. You go around this one but backwards, and then you come in and go around this one backwards, and then out, right? The fact that you're going around C2 but in the negative direction, and C0 but in the negative direction, well, these integrals cancel each other out because you're going in and out, and that goes in and out. And so the Cauchy theorem says that that all of this adds up to 0. So the integral on the big curve C plus the integral on minus C2 plus the integral on minus C0 must be 0. So the integral on the big curve on the outside can be reduced to two little tiny integrals. Okay, so keep that in mind. This is a direct consequence of the Cauchy theorem that we can replace big circles with little circles around isolated singularities. Why are we studying isolated singularities? Because we can do this. Okay, so these two basic facts, this is 2 pi I and this is 0, coupled together with this Cauchy thing, are going to underlie the three approaches to this problem. The first approach is the first one. So actually suggest some to me. What's the first obvious attack on this thing? Partial fractions. There we go. Beautiful. Partial fractions. So you look at that and you say, I bet I could do partial fraction expansion of this thing. If you do that, if you take 1 over z squared times z minus 2, I think it turns out to be equal to minus 1/4 over z minus 1/2 over z squared plus 1/4 over z minus 2. You do a partial fraction decomposition, that's what you get out the other side by doing the partial fractions. So this function and this function are the same function. So the partial fraction approach, which is approach 1, says that you're supposed to do this. The integral around z is equal to 4 can be thought of the big function, z squared, z minus 2 dz, can be thought of as the integral around z is equal to 4 of minus 1/4 over z plus the dz plus the integral z is equal to 4 of minus 1/2 over z squared plus the integral z is equal to 4 of 1/4 of z minus 2 dz. Now apply principle 1. What is the integral of 1 over z if that curve goes around the 0 that is its singularity? 2 pi I. So this one is minus 1/4 times 2 pi I. How about that one? It's not 1 over z, it's 1 over z squared. What's the integral of 1 over z squared on a closed contour? 0. By the parametric argument, right? What's the integral of this piece? Well, 1 over z minus 2, that 2 is inside the contour, so the integral of 1 over z minus 2 is 2 pi I. So again, we end up with 1/4 times 2 pi I. And the annoyance, oh, sorry, what does that mean? It means that this integral is nothing. Now the annoyance here is actually this step. See, I skipped all the hard-working, grindy part where you take this function and actually find its partial fraction decomposition. It takes a lot of work. Especially if these functions start getting bigger, that's really nasty. But approach 1 is sort of labor-intensive, but it boils this thing down into calculating in terms of simple linear pieces where the integrals will either be zeros or they will be 2 pi i's, basically. Whether if the function is analytic or has power higher than 2, you can just read that off. And all you have to tell is the 0 inside or outside the curve? Is the 0 inside or outside the curve? Is the 0 inside or outside the curve? And is the power 1 or something other than 1 in the denominator? Okay? So that's the partial fraction method. And its facility boils down to how willing you are to do this step. Okay, that's method 1, partial fractions. Is it okay if I leave the partial fraction computation aside for right now? Okay. What is method 2 going to be? That was partial fractions. How else could I do it? I could use the Cauchy integral theorem for derivatives, I think, is one way of doing it. And the other way I could do it is with the residue theorem. So I have 2 other approaches first. I probably want to end with the nicest one. So let's do the residue theorem next. So approach 2. Didn't I have an eraser? Oh. Okay. Actually, maybe we'll do the easy one next. Or maybe not. Okay. Approach 2. Let's use the residue theorem. What is the residue theorem? We haven't learned the residue theorem, but we've learned the one singularity theorem, right? The one singularity theorem says that if you had the integral around c of f of z dz, and this has one isolated singularity inside of c, c contains one isolated singularity of f, then this integral is equal to 2 pi I times the residue of f calculated at that isolated singularity. The coefficient of the z to the minus 1 term, right? That's what the one singularity theorem says. If that curve contains one singularity, then you can just compute directly by knowing what the residue is. Here I'm going to use this reduction, where I'm going to take the integral on the big set and turn it into a sum of integrals on the small sets, because that will isolate these 2 singularities all by themselves inside circles. Yep.
So even a higher order singularity is considered.
It's isolated. It could be essential, and it would still be isolated.
Okay.
The isolation just means that there's not some beam of branch points, like a branch cut sticking out of it, or some curve of singularities where things are bad. Or even worse, you could have a sequence of singularities that accumulate at some sort of limit point. Those aren't isolated because there's no neighborhood you can draw where there's only one singularity on the inside. Isolated singularity just means there's some circle you can draw of whatever size so that only one singularity is inside of it.
So then is it incorrect to think of like 1 over z squared as having 2 zeros at the origin?
What you should think is it has 1 0 of order 2 at the origin. So it's a single it's a single point that is bad, but the order of the badness is 2. Okay, so in order to use that singularity, I can't do this because the curve is wrong, right? This has 2 singularities on the inside, and we don't know the residue theorem yet, so I can't use it. So what we're going to do is we're going to replace this with the integral around 0 of 1 over z squared times z minus 2 dz, plus the integral around c2 of 1 over z squared times z minus 2 dz. I can reduce the theorem on the big contour into the sum of the integrals on the little 2 contours that go around those singularities. That's this argument, right, that I did earlier. Oh, I missed that. Right? Decayed tooth Pac-Man is what some people call this thing. Okay, so, he'll be back. Okay, so if I want to use the one singularity theorem, I have to be able to compute the residue of these things, which means I have to be able to compute their Laurent series. Damn. How about we do the easy one first? So the easy one is probably this guy. Because what that means is, if I want to compute the Laurent series of this function around, or sorry, this one, is that right? I want to compute the Laurent series of this function around 0. The singularity is 0, it's in the middle. So I'm going to think of this as 1 over z squared times 1 over z minus 2. And I'm going to write the Maclaurin series for this because the singularity I'm trying to isolate is 0. Here, z naught is equal to 0, so I'm looking for a sum of the form cn z to the n. I just want z to the n's in here. How do I do that expansion? Oh, man. 1 over z minus 2. Okay, so I get 1 over z squared times minus 1/2 of 1 over 1 minus z over 2. Now I can use the geometric series to say that this is minus 1/2 times 1 over z squared times the sum of 1/2 to the n, z to the n. Now I can multiply these bits in here, and I'm going to get, let's see, there's a minus 1, and there's a 2 to the n plus 1, and there's a z to the n minus 2, and that is a series calculated from 0 to infinity. This series was from 0 to infinity. So I multiplied the z squared in and subtracted it. I've multiplied the 2 and added it to this 2 to the n. And the negative 1 doesn't alternate, it's just a negative 1 floating around. What's the z? Okay, so what's the residue of this series? Well, it's the coefficient that goes with the z is equal to minus 1 term. So pick out the n that does that. So which value of n produces the one we want? Okay, so if I plug in n equals 1, I get minus 1 over 2 to the 1 plus 1 times z to the minus 1. And that value right there, that's the residue. It's the coefficient of the z to the minus 1 term. So the residue of f, that's not how you write it. The residue of f at 0 is minus 1/4. Yep.
So in general, when you're making the power series, you choose the piece that's not going to be where the singularity we're looking at.
Yeah, because this can get folded into the point is that's going to get folded into the Maclaurin series. This has to be re-expressed as a Maclaurin series. In the other direction, that can get folded into a series in terms of z minus 2. That has to be expressed in terms of z minus 2s.
Is it because those pieces aren't defined in the neighborhood?
Essentially, yeah. They're not analytic, so you have to throw them in at the end, right? There's no way that you're going to be able, I mean, that's not even defined at the point that you're calculating at. So if you're expressing this at 0, that makes no sense at 0, so you just toss it in at the end.
Gotcha, okay.
Okay, this was the easy series. Because the other one, okay, well, so, okay, what is the one singular? Let's just celebrate our victory here. This residue being equal to 1/4, what does the one singularity theorem say? It says that this particular integral must have been equal to minus 1/4 times 2 pi I. 2 pi I times the residue of f at 0. Well, isn't that the same thing we got when we computed it the other way? Okay, well, that's a good sign. It means we're probably doing something right. Okay, so now let's compute the other series. Ugh, all right. So now we need to do this one. We need 1 over z minus 2 times 1 over z squared expressed. It's not a chance, that's how you spell expressed. Expressed about z is equal to 2. Right? Yeah, okay. So after quite a bit of work, either writing a series for 1 over z at z minus 2, and then re-expressing it as a harmonic or a geometric series, or taking the derivative, doing 1 over z and taking the derivative, or you could use the binomial series expansion. There's like a lot of work goes into this, so you do some work. And what falls out is this: 1 over z minus 2, you can see all the work on my page here, times the sum from 0 to infinity. There's a 4 out here, and we have minus 2 choose k, 1 over 2 to the k, z minus 2 to the k. These are called the binomial coefficients. This is a pattern that basically follows the same pattern that you never seen this before? Oh, the binomial series. How did I write combinations with a negative number up top?
Yeah, that's
N choose k. N choose k is actually a defined formula for any n. And the way that you do it is you write n times n minus 1 down to n minus k plus 1, and then divide by k factorial, which you could put any number into that, and it works. So this is a generalization of the combinations, but where you can put any number in for n. So for example, 1/2 choose 3 is equal to 1/2 minus 1/2 minus 3/2, because you subtract 1 and subtract 1, and then you divide by 3 factorial. The reason that you get these is because these are the coefficients that come out of taking repeated derivatives. Yep.
So can you have any number you want for k then?
K has to be integers because it's the index set of a sum, right? So the k's are going to be integers. That has to be an integer value, at least in this generalization.
Oh, there's other ways?
You can take any of these formulas and blow them up to any I mean, you can make them continuous if you really want to, but that'd be crazy. So these are called the binomial coefficients.
So if I go to Desmos and I grab x factorial.
Okay, or you could do the derivative method. The point is, suppose that you actually ran this calculation, you get this series. Remember, this is just a formula, right? It's just a formula. It's just a formula, that's all it is. So you put these guys inside, and what do you get? The sum from 0 to infinity of this minus 2 choose k weirdness. And then what we get, a 1 over 2 to the k minus 2, and a z minus 2 to the k minus 1. Oh wait, this 4 is down here, sorry, my bad. There's the 4, so it's plus 2. Okay, which term, what power of what k value, if k goes from 0 to infinity, what k value do you plug in to get the z to the minus 1 term this time? 0, okay. So, minus 2 choose 0, which is always 1 still. 1 over 2 to the 0 plus 2 times z minus 2 to the minus 1. So that's 1/4 z minus 2 to the minus 1. What's the residue at 2? Again, tons of work goes into computing this, right? Getting this series takes a lot of work, either whether you do it this way with the binomial formula or you do it the other way with the derivatives. There's a bunch of work that goes in here. Yep.
How do you get it with how do you get from 1 over z squared to that pumpkin mess?
So basically x plus 1 to the alpha
Okay.
is equal to the sum from k equals 0 to infinity.
Oh, it's just binomial extension.
It's literally the binomial expansion, but with the generalized coefficients.
Okay, gotcha.
That's all it is, right? Alpha choose k, z minus, or z to the k. That's all it is. It's just the binomial expansion.
Where'd the 4 come from, though?
The 4 came from the fact that if I manipulate this so that it looks like 1 plus something, I have to put a plus 1. I really need a minus 2 right here, right? You really going to make me walk through this? Z is equal to z minus 2 plus 2, right?
Okay.
So z is also equal to 2 times z minus 2 over 2 plus 1. That's starting to look like something I could use the binomial theorem on.
Okay.
But this was all squared because it was a z squared.
Okay.
So the 2 pops out and turns into a 4.
Cool.
That's
okay.
It's just that manipulation to use this. The point of all of this is, this kind of sucks, right? Computing these series kind of sucks. Okay, so, but notice, we won, right? We won because we found the residue after all that. Like, this took me 20 minutes to derive this in class, right? Or in my office. So, but we still won because we got the residue. There it is, the residue of f. The residue of f at 2 is equal to 1/4, which means I can say that this is equal to 1/4 times 2 pi I, and then I add them together and I get 0 again. Okay, now those methods are supposed to convince you that there must be a better way to do this, right? All right, before I go on, are there any questions about how I did any of this? Okay, next method. So I would call this one calculation by the residue theory. You should hope that there's a better way to compute residues. That's really what you should just be praying, like, please, maybe in chapter 3.3 they'll teach an algorithm for computing residues that doesn't require having to do this crap. And if you go look in the book, you'll see that there is an algorithm for computing residues that doesn't work this way. Okay, that was method 2. Now let's use method 3. And you should appreciate now that you've seen these long-winded ways of doing this. Here's method 3. What have we not used yet? What method have we not used yet? Cauchy integral theorem. Oh, for derivatives, right? So this is the best way to do this problem. Okay, here you go. Here you go. Remember that this curve, the integral on that curve boils down to the integral around this one plus the integral around that one, right? C0 and C2. With one single isolated point inside each one. Okay, nobody did it this way, which is kind of... Nobody I've seen so far has done it this way. So, the integral around C of 1 over z squared times z minus 2 dz is equal to the integral around C naught of, is there an analytic piece of that function?
Yeah.
What is the piece of this function that's analytic at 0? 1 over z minus 2 over z squared dz plus the integral around C2. Is there a piece of the function that's analytic at 2? 1 over z squared over z minus 2 dz. But this, if I call this function right here f, and I call this function g, what is this equal to? I have a function that's analytic, and there's a z minus 2 in the denominator, so what does the Cauchy integral theorem say this is equal to? 2 pi I g of 2. Oh, so it's 2 pi I times 1 over 4. That was easy. How about the other one? Ah, but there's a z squared in the denominator. What the hell am I going to do? Oh, the Cauchy integral theorem of derivatives. So what is this one equal to then? 2 pi I over 1 factorial, because this is the first derivative formula. So we're going to use the Cauchy integral theorem for derivatives here. 2 pi I over 1 factorial f prime at 0. Remember, the 0 that we're sticking in here is that isolated point, right? This is what the formula is set up. This is z minus 0 down here. So the square indicates that you're working with the derivative formula. The singularity is 0. That function is analytic, so you just plug it in. What does that equal to? 2 pi I, okay, f of 0 is minus... So, oh man, okay, so, man, I gotta compute a derivative. F of z is equal to 1 over z minus 2. So f prime of z is equal to minus 1 over z minus 2 squared. Okay, so this is 1/4. Negative. Oh, so it's minus 1/4 2 pi I. I don't know about you guys, but this is way easier than the other ways we did it, right? Like way easier. So every one of these problems can be thought, I mean, so the big tool set of the class is that this approach to integration, we have lots of ways of attacking each question. And it's worth taking the time to think, boy, if I can do this and get 0, is that the way to go, right? And I don't think I ever pointed out formally in class that you can always do this. Cauchy's theorem says you can always reduce a function with isolated singularities to integrals around the singularities individually. And that's a trick that you should use when you can use it, because it's a way of reducing the complexity of what you're working with. And if it's a meromorphic function, and in particular a rational function, you can always do this crap, where you take the analytic piece and shove it up into the numerator, and keep the part that's not analytic in the denominator. All right. That's it. See you guys. I will also point out as a last-minute note here that in response to me playing mathematical tennis with myself between Caleb and Madison and Trevor and everybody last time, that I wrote like an over-the-top post on the Canvas page answering the question about why e to the z cosine of 1 over z has an essential singularity. So you should take time to read it. It's a cool theorem.